Hello students, in this lecture number 3 we are going to study about errors and error propagation. Now first we will understand what is the concept of significant digits. Now as you could see in this diagram, okay, if you see this particular odometer, whatever is shown here, okay, what is the if one asks you that what is the reading, okay, naturally you can identify or you can answer that it's 48. But if you take a closer look of this, then you will find that this scale is indicating 48 and plus few digits more than that. Okay, it's more than just 48, so you can say that it's a 48.5. So this is called as significant digit, concept of significant digit. That is, it has got three significant digits that with surety I could say that the reading is 48.5. So it is a conventional to set up the estimate digit 1/2 of the smallest scale division on the measurement device. You know this, okay? Because of this, we can say that the speedometer reading would be having three significant digits, that is 48.5. So this is a example of significant digit. Now let us study about errors and approximation, into which we will first understand the concept of numerical error, accuracy and precision. So if you look at this diagram, okay, it has got it's a dartboard, and in which let us say 4 attempts were made. Okay, so if you see that this figure A, okay, it is inaccurate and imprecise. That means it is not accurate as well as it is not precise. Now in figure B, okay, it is shown that it is sometimes it is accurate. That means someone it has hit over here, so it is accurate but it is not precise. Now figure C indicates that it's precise but it is not accurate, that is not hitting a target properly. Okay, in figure D, which indicates it is accurate as well as it is a preciseness. Okay, so if you remember that what exactly the accuracy is, so accuracy refers is how closely the computed or measured value agrees with the true value, that is called as accuracy. And precision refers to how closely individually computed or measured value agree with each other, that is precision. So numerical errors are nothing but the errors arise from use of approximation to represent the exact mathematical operation and quantities. The errors are associated with both calculation as well as measurement, can be characterized with regard to their accuracy and precision. So depending on what is accuracy and what is precision, that we just seen. Okay, so numerical error, again it is because of the approximation. So the formula for true value will be true value is equal to approximation plus error. So that indicates that true error will be equal to true value minus approximation. So percentage relative error formula will be given by true error upon true value multiplied by 100. Now all these formula you already learnt in your physics. So let us have a problem. Okay, the problem statement says that suppose you have a task of measuring a length of a bridge and a rivet come up to 9,999 and 9 centimeter respectively, whereas the true lengths are 10,000 centimeter and 10 centimeter respectively. So you need to compute what is the true error, and then you need to compute the true percent relative error in each case. Okay, let us say you are measuring a rivet and you are measuring a bridge. Okay, for both measurement you have 1 centimeter error, but you need to how severe it will be, that is can be easily demonstrated by use of this example. Okay, so the error in measurement of bridge is 1 centimeter. Okay, and the error in the measurement of rivet is also 1 centimeter, but the percent relative error in the bridge will be given by 1 upon 10,000 into 100 percentage. So it will be 0.01%, whereas for the same 1 centimeter measured error, it is 10% of the rivet's length. So this 10% is more severe. So you can use a tape to simple tape to measure the length of a bridge, but you cannot use the simple scale to measure the length of a rivet. For measuring length of a rivet, you might be needing vernier. Okay, so this example will tell us that why the context is more important in case of measurement. So the approximation is nothing but in real world application, we know we will not know the true answer a priori. For these situations, an alternative is to normalize the error using the best available estimate of true value, that is the approximation itself. So because of which we can say that percentage approximate error is nothing but approximate error upon approximation into 100 in terms of percentage. One of the challenge of numerical method is to determine error estimates in the absence of knowledge of true value. A present approximation is made on the basis of previous approximation. The process is performed repetitively or also called as or iteratively to successfully compute better and better approximations. So this is how we progress. So this iterative is a word which we are going to hear more and more often in this particular subject. Iterative means repeatedly. So because of which we can have a formula for percentage relative error is equal to current approximation minus previous approximation upon current approximation into 100 in terms of percentage. So let us have an example of Maclaurin series. Okay, you know that Maclaurin series is given by this particular formula of e raised to x is equal to 1 plus x square by 2 plus x cube upon 3 factorial plus so on plus x raised to n upon n factorial. So for start, we can say that we'll have a value of e raised to x as 1. Okay. So this is the approximation. E raised to x is equal to 1 is approximation, and from there we need to find out what is e raised to 0.5 using this formula of this series. Okay. So let us say that e raised to x is equal to, if we consider only first two terms of this particular series, then for x is equal to 0.5, e raised to 0.5 value is 1.5. Okay. But we all know that e raised to 0.5, let us say a true value is 1.648721. This is the true value for e raised to 0.5. Then percentage true error will be 1.6487 minus 1.5 upon 1.648721. So that will come up to 9.02 percentage. Okay, so from here we can say that approximate error will be given by your current approximation, that is 1.5, minus previous approximation, that is 1, upon current approximation, that is 1.5 multiplied by 100, that will come up to 33.3 percentage. Now when we go on adding the number of term in the series, like first 1 plus x, then if we add another term of x square upon 2 factorial or x square upon 2, okay, then we get a term. When we add a second term, we get result as 1.5, okay, where the true error will be 9.02 percentage and approximate error will be 13.3%. Now how this 9.02 is calculated? This is nothing but the, what you can say, this is nothing but the true value 1.6487 minus 1.5 upon 1.6487. That will be giving you 9.02 percentage. Now approximate error in this case will be equal to this 1.5 minus 1 upon 1.5 into 100. That will give you 33.3%. Okay. Now for the when you add three terms, you get result of 1.625. Then you get true error, percentage true error of 1.44%, then 7.69%. As you go on adding terms in the series of x e raised to x, okay, this error is going to decrease. If you add the third term of e raised to x upon 3 factorial, then this will be the answer. Then another term, this will be the answer. Then another term, this will be the answer. Now here everywhere you find that this true error is going down, okay, as well as this approximate error is also, percentage approximate error is also coming down. Okay, so there must be a stopping criteria, that how many terms you will use in this formula. So in general, we will stop the operation when the process continue till approximate error comes below true error. That is, this approximate error, if it is less than true error, that means we have reached up to true value and we will stop. So called this is called a error propagation. So let us see few examples of round off error. So round off errors are originate from the fact that computers remain only a fixed number of significant digits. Okay, so round off errors has a few different types, like chopping error, rounding off, machine error, and manual error. Chopping error means example is that 2.34567 is chopped to 2.345. That is, we have completely neglected the rest of the digits. Then this is called as a chopping error. Rounding error is 2.34567 is rounded up to 2.346. Then machine error is because of the storage capacity of the computer, and manual errors are because of the manual mistake, like instead of writing 2.45789, if I write 24.5789, then it's a manual error. So let us see with the help of an example. So the problem statement says that round off error number is round off the number 66250 to the 4 digits significant digits and compute the absolute and relative percentage error. Now let us say this is your number of 66250 and we need to round it off to 4 significant digits. Okay, so 4 significant digits means 6.625. Okay, so this is your rounded off value, 6.652. Okay, so here you could see that absolute error will be nothing but this value 6.65250 minus 6.652. Okay, so this will be absolute error will be 0.0005. Now relative error will be 0.0005 upon 6.65250, that is the true value. Okay, so that comes 75 into 159 into 10 raised to minus 6. So if you multiply it by 100, okay, you will get a percentage relative error that comes up to 0.0007 percentage. So similarly, you can go for this example. Okay, I'll not elaborate it in this video, but this PPT is available to you, so you can always go on and work out on these particular examples. So let us see about error propagation. So error propagation during the calculation appears when the next approximation is based on the previous approximation. This is most important. Whenever the next approximation is based on the previous approximation, naturally the error will get propagated. So let us see this example of calculation of a volume of a solid. If it is given by V is equal to 6.4 into xy square upon z square, where xyz denotes the dimension of that solid, then if we have a error of 0.001 plus or minus in the measurement of x and y and z, then we need to find out what will be the error in the measurement of volume. Okay, so for that, let us see this particular example. So this take a partial derivative of v. Okay, so delta v is equal to da by f upon da by x into delta x, da by f upon da by into delta y, plus da by f upon da by z into delta z. Now epsilon x, epsilon y and epsilon z, both all these three things are given. Okay, it is 0.001. Now here 6.5 xy square minus da by f by da by z. So here there will be minus sign. Okay, so because of this you could see that this value is there. Okay, so we just take a partial derivative and put the values of epsilon x, epsilon y and epsilon z. You will get delta v is equal to 0.0448. Okay, so if you have a measure of error of 0.001 in the measurement of x, y and z, you will have the error of 0.0448 in the measurement of volume. So this is the simple example. Similarly, this example of calculation of the deflection at the center point of the beam is shown over here. This is a case where the beam is uniformly loaded, UDL. Okay, it is simply supported at the both ends. Okay, so you need to find out that if there is an error in the measurement of length of this beam, there is a measurement in error of E, that is modulus of elasticity for this beam, then the measurement in the area in the measurement of moment of inertia I of this beam. If these three quantities are measured and having their inherent error, then what will be the error in the deflection of this beam from this center, that is y, deflection of the beam. What is the deflection? So that numerical is explained over here. So this is nothing but da by y by da by f into delta f plus da by y by da by l into delta l minus da by y by da by e into delta e and da by y by da by I into delta I. So here both these sign will be minus. Okay, and if you differentiate partially with respect to each this variable, independent variable, you will get uh, this expression. Okay, and if you put the values of all these variables of delta x, all these delta e, delta y, if you get, then sorry, delta e, delta I you put, then you will get the value of delta y, that will be this much. Okay, so if you get delta y, then what will be the minimum and maximum of the deflection that you need to find out, that is what will be the minimum maximum, just by putting these two values. Okay, addition and subtraction, you will get y as 0.15243 and then 0.175507 meter. So if you do it for calculation, if you take this value as a length, the value of L, okay, and you put the values again in the equation, you will get minimum and maximum deflection of the beam. Okay, now let us study about relevance of error propagation to numerical methods. So truncation errors are those that result from using approximation in place of exact mathematical procedure while calculation. A truncation error was introduced into numerical solution because of the difference equation only approximates the true value of the derivative. That means, let us say take an example of Taylor theorem. Okay, so in the Taylor theorem you could say that f of xi plus 1 is nothing but f of xi plus f dash of xi into h plus f double dash of xi upon 2 factorial into h square and so on. So this Taylor theorem is known to you. So we can choose how far away from x we want to evaluate f of x. and we can control the number of terms we can include in the expansion of this series. Okay, so that is nothing but the order of error. So the truncation error is decreased by addition of number of terms in the Taylor series. That if we go on adding the number of terms in the Taylor series, we are going to get lesser and lesser truncation error. So, but whether it is always desirable to have a, a, very small step size in order to reduce the truncation error, we will see that with the help of this diagram. Okay, so the total numerical error is summation of truncation error plus round off error, that we know. So in general, the only way to minimize the round off error is to increase the number of significant figures of the computer, and round off error will increase due to subtractive calculation or due to increase in the number of computation in an analysis. In computation, we could conceivably decrease the step size to minimize truncation error, but only to discover that in doing so the round off error begins to dominate the solution and the total error again grows up. Hence the truncation error are decreased as the round off errors are increased. So in this diagram you can see this point of diminishing returns, and this is the step size. Okay, so when we reduce the step size, okay, the truncation error will go down, just because we have seen that we are adding more terms to the Taylor series, the truncation error will come down. But at the same time, when truncation error is coming down, the round of error is going to increase. So this round of error is going to increase, this curve. Okay, round of error is going to increase. So at the minimum very small step size, you may have a very less truncation error but very large round of error. Okay, so as a and when you decrease when you increase the step size, okay, the round of error will go down, but at the same time the truncation error will increase. Okay, so these are two contradictory objectives, and you need to find certain point where this is called as a point of diminishing return, where the truncation error and round off error will balance each other. So that is what is stated in this diagram. So this completes your discussion about errors and approximation. Thank you.